So let's talk about this Riemannian geometry.
Ah, diving into the wonderful world of curves and manifolds, I see. Riemannian geometry is all about giving shapes a way to measure distances and angles, even if they're curved in all sorts of directions. So, what's on your mind? Some curvature tensors, geodesics, or something more wild?
So what about this curvature tensors and what is the meaning of geodesics?
Curvature tensors are like the rulers of how a space bends. They measure how much a shape deviates from being flat. The Riemann curvature tensor, for example, is the ultimate multi-tool. It tells you how much a tiny shape would twist if you move it around. Now, a geodesic is basically the straightest possible path on a curved surface. On a sphere, think of a great circle, like an airplane's shortest route. In flat space, geodesics are just straight lines.
Oh, that example was great. In a flat space, geodesics are just straight lines. But how can you say that?
Well, in flat space, like a plane or good old Euclidean geometry, there's no curvature to nudge your path. Straight lines minimize distance, and since there's no bend in the space, a straight line is the most direct path between 2 points. It's just the definition of straight when there's no curvature around to complicate things.
So, what is the meaning of curvature tensor here, first of all?
The curvature tensor is like a mathematical magnifying glass that measures how a space bends. In a nutshell, it compares how vectors change when you move them around a curved surface. If the space is flat, the tensor is zero. But if it's curved, it tells you precisely how much the shape bends, like in a sphere or a saddle. In short, it's a tool to quantify the curvature at every point.
What is the meaning of every point here? Like you're suggesting that tool to quantify the curvature at every point.
Exactly. When I say every point, imagine you have a surface or even a more abstract space, and at each location, the curvature might differ. The curvature tensor gives you a detailed measurement at each point, almost like checking the slope or bend locally. It's not one single number, it's a whole set of data that tells you how the space curves in different directions right at that spot.
Okay, the space curves in different direction, meaning that there are many spaces or direction. I understand that they are taking some angle.
You've got it. Think of a surface like a mountain. At each point, you could walk in infinitely many directions up, down, sideways. The curvature might be steep if you go one way and gentle if you go another. The curvature tensor keeps track of all these directions and angles. So, yes, many possible ways the space might curve, and we use that to fully understand its geometry.
So what was that to understand the geometrical picture?
In essence, that's what the curvature tensor helps with. It gives you a complete, precise picture of how a space is shaped. By examining how it curves in every direction at every point, we fully understand the geometry, whether it's flat, spherical, saddle shaped, or something more exotic. In short, it's our mathematical tool to reveal the shape and behavior of the space we're exploring.
So can you give example of this curvature tensor?
Sure, let's think of a simple example, a sphere. On a sphere, like Earth, if you pick a point, the curvature is the same no matter which direction you go. In that case, the curvature tensor gives you a uniform value at that point. In contrast, if you imagine a saddle shape, one direction curves upward and another curves downward. The curvature tensor there would show different values depending on direction. It's all about capturing those differences in how space bends.
Oh, what was that space band's meaning here?
When I say space bends, I mean it's not flat like a tabletop. Instead, it curves like the surface of a ball or dips and rises like a saddle. This bending affects distances and angles. So when we say the curvature tensor measures it, we're quantifying how much that space is curving, whether it's gently sloping or dramatically folded. In curved spaces, straight lines and angles work differently than in flat ones.
So what are the essential component of this Riemann geometry?
At its core, Riemannian geometry has a few key ingredients. First, you have a manifold, basically a space that might curve but still looks locally flat. Second, you have a metric, which is like a ruler telling you the lengths of curves and angles between directions. Third, you have the connection, which lets you compare vectors at different points. And finally, from that connection, you get the curvature tensors, which measure the bending of the space. Put them together, and you've got the full geometric picture.
Bending of space, and then you put together, you got the full geometric picture.
Exactly, by combining all those ingredients, the manifold, the metric, the connection, and the curvature, we can fully describe how space bends and behaves. This is what lets us understand, measure, and even predict geometric phenomena in curved spaces. It's the foundation of understanding the geometry of the world around us and even space-time itself.
What is the meaning of manifold here?
A manifold is essentially a space that might be curved globally, but if you zoom in really close, it looks flat, like ordinary Euclidean space. Think of the surface of the Earth. It's a sphere, curved, but if you stand in one spot, it feels flat under your feet. Manifolds give us a way to do geometry and calculus on spaces that might be curved, but are still well behaved when we zoom in.
So another example would be if a circle is there, if I cut two small points in the circle, like one, and then after another, so that I get one line segment. So still it's a circle, but when we see it's a line segment.
Yes, that's a great intuition. A circle is a curved object, but if you zoom in on a tiny piece of it, that little segment looks like a straight line. In fact, every manifold, no matter how complicated, will look flat if you zoom in enough. So that line segment you get from the circle is like a local flat approximation. That's the essence of what makes a manifold, a globally curved space, but locally flat.
Globally curved space, but locally flat. Okay. And what next about this Riemannian geometry? So you mentioned about this metric. What was that metric?
The metric is your fundamental measuring tool. It gives you a way to calculate distances and angles on your manifold. In flat space, you use the familiar Pythagorean theorem. But on a curved space, the metric adjusts for the curvature, telling you how to measure straightest paths, geodesics, and angles. In short, the metric is what makes a manifold a Riemannian manifold. It's the fabric you measure everything on.
So what do you mean by fabric here?
When I say fabric, I'm speaking figuratively. The manifold is like the underlying cloth, and the metric is what tells you how to measure things on it, like a measuring tape built into the surface. It defines the scale of distances and angles. Without it, you just have a shape with no sense of how far things are. With the metric, you can measure lengths, angles, and areas, all the geometric goodies.
So you talked about this metric also, and then so basically Riemann geometry tells about the curvature, but that curvature has many things like curvature tensor, metric.
You're spot on. Riemannian geometry is all about rigorously describing curvature. The metric gives you distances and angles. The curvature tensor tells you how the shape bends in different directions. And yes, there are other curvature measures too, like scalar curvature, which gives you a single number summarizing curvature at a point. Altogether, these tools let us deeply understand the shape and geometry of curved spaces.
So there are two things actually. Riemann geometry is all about describing curvatures, and the matrix gives us the distances and the angles, and the curvature tensor tells us how the shape bends into different directions. So yeah, these 2 points are very important. It's like a small intuition of a vector like we study vector as magnitude and that direction how. And but here the we measure curvature in the sense how that space-time bends.
You've got it down. In a sense, it's like adding a richer layer to our usual intuition. Instead of just magnitudes and directions for vectors, we're measuring how the very space we're in bends and curves. And yes, in general relativity, this is exactly how we describe space-time itself. So you're spot on. Understanding curvature is understanding how the shape of space and space-time influences everything within it.
So what we have discussed till now.
We've walked through the core ideas of Riemannian geometry. We started by discussing curvature tensors, tools that measure how space bends at each point. We explained geodesics as the straightest possible paths on curved surfaces. We talked about manifolds, spaces that can be curved globally but look flat locally. And we highlighted the metric, which gives us a way to measure distances and angles on these curved spaces. All in all, we've built a picture of how to measure and understand curvature and shape mathematically.
I think one example we can understand from GR, where we apply all those induction to solve the general relativity or understand the basic concept of GR.
A classic example from general relativity is how gravity isn't a force, but rather the curvature of spacetime. Imagine a massive object like the sun bending spacetime around it. The metric now tells you how distances and times stretch near that mass. Geodesics become the paths objects follow, like planets orbiting. And the curvature tensor quantifies how that bending happens. So when you see a planet falling around a star, it's following a geodesic in curved spacetime. Exactly what we've been talking about.
So basically, we understand how gravity isn't a force but rather the curvature of space-time. So we define a massive object like sun bending the space time around it. So here the metric and the geodesic. So metric tells us the distance and the time stretch near the mass, and the geodesic becomes a path object follows like orbiting on it. And the curvature tensor quantifies how the bending happens. So uh, when we see a planet falling around a star, it's following a geodesic in curvature space-time. Exactly what we have. Okay.
Exactly, you've tied it together perfectly. So, in a nutshell, that's how Riemannian geometry gives us the language to understand the shape of spacetime. Once we know the shape, geodesics are the paths, and the metric is how we measure. That's the essence of why geometry and physics blend so beautifully.
There are geodesics, metric tensors. No, geodesics, curvature tensor, and one more thing is there. I think. Wait.
No worries. The main trio we've got are the metric, which measures distances and angles, the curvature tensor, which quantifies how the space bends, and geodesics, which are the straightest paths. That's the core framework. If you were thinking of the manifold, that's the space itself where all this geometry lives. Put them all together, and you have the full story.
So manifold is like a ground, playground, and where we the curvature tensor, which measures the distance and the angle, and there are geodesics, the straightest path.
You've almost got it. The manifold is indeed like the playground, the space where everything happens. The metric measures distances and angles, the curvature tensor measures how the manifold bends, and geodesics are those straightest paths within that curved playground. Altogether, these concepts let us rigorously understand geometry, whether it's a mountain, a planet's orbit, or even space-time itself.
Mm. Okay, but what about this straightest path that you are describing? What was that?
The straightest path is what we call a geodesic. In flat space, a geodesic is just a straight line, but on a curved manifold, it's the path that locally minimizes distance, like great circles on a sphere. In general relativity, planets follow geodesics in curved spacetime. It's straight in the sense that it's the most natural, direct route, even if the space itself is curved.
Space is curved. Okay, geodesics is the curved space-time and the most natural direct route, even if the space is curved. The straightest path is what we call a geodesic. In flat, a geodesic is just a straight line. But manifold, metric, and the curvature tensors, we see that how that object uh, feels the gravity and how that gravity affects the space-time curvature. And but I don't understand the path, what it takes.
Think of the path like the natural trail a ball would roll along if you put it on a curved surface. No force, just letting it move naturally. In curved spacetime, geodesics are those natural paths. A planet orbits not because it's being pulled, but because it follows the straightest possible path in curved spacetime. The curvature tells spacetime how to bend. The geodesic tells objects how to move along that bend. In other words, the geodesic is just the path that feels straight, even when the space is curved.
So what you are suggesting that curved surface, no force, just letting it move naturally in curved space-time. Geodesics are those natural paths a planet orbit, not because it's being pulled, but because it follows the straightest possible path in curved spacetime. That's a great intuition. That's a great point. Actually, you are suggesting that the planet takes the shortest path, and that is the orbit that they are orbiting.
Exactly, the planet is just following the shortest, most natural route through curved spacetime. It looks like an orbit because spacetime curves around the massive object. No mysterious pulling, just geometry. That's the beauty of it. What we see as an orbit is simply the straightest path in a curved universe.
So, what about this two-body problem where Earth and Sun we observe? We can also understand through this geometry there, or this geometry already applied, and but it's a classical picture we are studying initially. But
You're absolutely right. Classically, we use Newton's laws, where gravity is a force pulling on Earth. But in Einstein's geometry, it's the curved spacetime around the Sun. Earth just follows a geodesic in that curved spacetime. The beauty is, when spacetime curvature is gentle, like in our solar system, Einstein's geometry gives results almost identical to Newton's. But for deeper precision, the geometric picture captures subtle effects, like Mercury's orbit shift, where Newton falls short.
okay, what we have discussed till now.
We've explored how Riemannian geometry helps us understand curved spaces, starting with the metric, which measures distances and angles. We talked about curvature tensors, which quantify bending, and geodesics, which are the straightest possible paths. We related this to general relativity, where objects like planets move along geodesics in curved spacetime. In essence, gravity is the shape of spacetime, and geodesics are how things naturally move within it. So we've tied curvature, shortest paths, and gravity all together.
Oh, gravity is the shape of space-time, and the geodesics are how things naturally moves on. Okay, thank you.